So,
Yes.
Najib, can you hear us? So, Najib, we cannot hear you, but we'll assume that you're able to see us and you're able to hear us. So, we'll continue with our meeting. Let me welcome you both, Emmy and Najib. Today, we are going to start our unit number 3. In unit 1, we discussed rate of change and all of the concepts which are very necessary for us to understand derivatives. And in unit 2, we actually took up limits and we understood what gradients and limits, how they work in together, and how do we find rate of change at any point on the curve. And now in unit 3, we'll discuss about derivatives, right? Since you've done a lot of practice earlier on with rate of change and gradient type of questions, you shouldn't really find this particular unit difficult. And rather, you'll find it very interesting. And at times, I see students asking me questions, why was this not introduced to us earlier, right? Anyway, let
Yeah.
me share with you the screen and then we'll see why we did not share this with you. So I hope both Najib and Emmy, you can see my screen.
Yeah.
This is on the derivatives, right?
Mhm.
Now, the first lesson on derivatives, what we learned is this difference quotient equation, which is given right on the top, right? So see this difference quotient equation,
Yeah.
dy, oh, okay. See only the right side of this difference quotient equation, which is so familiar with you. Perfect. Now, we have been calling this as the gradient equation. If you have to find gradient at any point on the curve, you could use this using a instead of x. So at that point, x will be equal to a. You could also use it as a gradient of the function because you know gradient is a function. Now, application of gradient is huge. Rate of change is something which we are trying to figure out in so many different applications, may it be chemistry, biology, physics, economics, anything, right? So rate of change is a very common term. And therefore, we have a new name to it, and that name is derivatives. So derivatives is more or less the same thing as we were talking about gradient. The only thing is we'll have a different nomenclature here. We write derivative in two different forms. One is dy dx, and the other one is f dash x. So I'll just introduce you to both the forms in a minute. Before that, let me tell you what we are going to talk about in today's session. We'll discuss the basic concept of derivatives. What is derivatives notation, differentiability, power rule, constant multiple rule, general power rule, sum and difference rule for derivatives. And we'll take up examples based on tangents and normals, and also one on rate of change. Now, ME for GCSE course, this is one of the most important chapter on calculus. Half of your questions are based on this chapter, so you need to really understand it and practice, okay?
Okay.
Now, to begin with the concept itself, we know that the gradient g of x was defined as limit of a function f of x plus h minus f of x over h, where h is approaching 0. We got this expression by bringing the 2 points very, very close so that the slope of the secant line matches with that of the tangent line, right? And that is how we define a gradient. Now, the same definition applies to most of the rate of change questions, and it is so popular that we are giving it a different name, which is called derivative. And the symbol being used will be f prime x. We call this as a prime notation also for derivatives. But the expression on the right-hand side is exactly same as what we have been doing. Perfect. In case we want derivative at a particular point, then x is replaced by a. X equals to a represents that particular point, correct? So derivative, as you can see here, is exactly same as the gradient itself. Now let's talk about two very popular notations which you will find in most of the books. Now in one of the, there are two things which I like to mention here. First, we are saying derivative at a point, and the second thing which we talk about is derivative in general for the function. So when I write a, that means we're talking about a point where x is equal to a. But if I don't write a, that means it is x. So we just treat it as a general derivative of the function itself. Now, one of these definitions, we use f prime x. Now, this is called prime or Lagrange's notation. Okay, so these are the two names. For simplicity, we just call it a prime notation, but the scientist's name has been honored, and Lagrange's notation, it is very popularly known as. The other one is we use dy dx, and this is called Leibniz notation. Strictly speaking, it is d dx of y, d dx of the function f of x. You understand? So d dx, d over dx, we say d dx or we say dy dx. Is that okay?
Mm.
These are the two notations which we are going to use in our discussions on derivatives. Right hand side, again, is the same thing. Limit of f of a plus h minus f of a over h, where h approaches 0, right? So very, very close those 2 points are, right? So with this, let's begin and see how it works. I've taken one example to illustrate how we are bridging the gap between what we know about gradients and what we are going to do in derivatives. So in example number 1, we're saying we'll find derivative of a function and gradient at a point. The question here is that we are given a function f of x equals to x cubed plus 1. Now, to understand it better, I've also shown the graph of this particular function, cubic function, which has been moved 1 unit up. Okay?
Mhm.
We need to find two things about it. First, derivative with respect to x, which we write as f prime x in our prime notation, right? Using first principle. So derivatives, basically, we need to find using the first principle. But once we learn some rules, then we'll apply the rules, and straight away, applying the rules, we'll get the answer. Now, it is such an important concept, so it becomes necessary to work with the rules, since first principle really takes a lot of time. And part B is to find the gradient of the curve at a particular point, and the point chosen here is P, which is 2, 9, shown here. Perfect. So first half of it is absolutely clear. To find the derivative at a point is same as to find the gradient at that particular point. Perfect. So to begin with, we'll find derivative of the function in general. So we are writing that we know that the function f of x is given to us. F of x plus h will be replaced x with x plus h in your expression. And so using the difference quotient formula, we'll just substitute the function itself in it, and x plus h whole cube is being expanded here, and then you simplify the terms. And what you get is all the terms in h, take h common and cancel with the denominator. You get an expression where you could substitute h equals to 0, and there you go. You get your derivative, which we were calling till now as a gradient, right? Or a rate of change or instantaneous rate of change at places. So f dash x is 3x squared. So that becomes the gradient of the curve. Now, we'll do part B, which is to find the gradient at a point p equals to 2, 9. X value is 2. So we'll replace x with 2, right? So we have replaced x with 2. See the notation, f prime of 2. Derivative at x equals to 2 is replace the x with 2, and you get 3 times 2 square, which is 12. So the derivative at x equals to 2 is 12. Is that clear to you?
Yeah.
Exactly same. The only thing which we have done is change the name from gradient or rate of change or instantaneous rate of change to derivative, and the notation will be dy dx or f prime x. Is that clear?
Mhm.
Now, coming back to the notation, we have seen two different notations. One, we write dy dx, and then we write f prime. However, dy dx is a very good notation to be used, since you know both the variables we are talking about. X is the independent variable, y is the dependent variable. Sometimes in an equation, you may have more than one variable. In that case, it makes sense to clearly write down what we are differentiating one with, right? But the variable in single variable calculus, which is our main objective at present, it doesn't make much difference. So for convenience, we use the prime notation rather than dy dx most of the time. Correct? But dy dx is a preferred notation. Sometimes we also use capital D or capital Dx to represent derivative of a function, right? So we will be using that sometimes. Now, if you want to find derivative at a specific point, then you have to mention the x value of the point as mentioned here in the form of f prime a. Remember, gradient of a curve at any point is the value of the derivative at that point, correct? So when I say find the gradient at this point, it is interpreted as instantaneous rate of change or slope at that point, which is the value of that derivative at that point. Now, since we have a derivative, it is not necessary that we'll always get a derivative of each and every function. There will be many circumstances where derivative cannot be found. It may not exist, mainly because the limit may not exist at that particular point for the slope of the tangent line. So these are a couple of examples which broadly gives you an idea. Where will the function have a derivative or will not have a derivative? So we actually discussed this earlier also while talking about the gradients. So as you know, if you have a cusp or a corner, as you have in absolute function or in radical or thirds, x to the power of 2 over 3 times, in that case, we are not sure about the slope of the tangent line as we move from left to right. There could be many different tangent lines at one particular point, and we say that does not exist. Now, in this square root function, here, if you try to figure out, it is like a vertical tangent line. That vertical tangent is also not defined, and therefore we say the derivative does not exist. You have a discontinuity, as shown in the last graph here. In that case also, at the point of discontinuity, we cannot have the derivative. One important thing here is, you can only find derivative on the domain of the function. If there is a point which is not in the domain, especially if you have an asymptote, for example, then we cannot have a derivative at that particular line, which is an asymptote, or we cannot have a derivative for any hole since it is not in the domain, right? So you cannot draw a tangent at that point. That's the whole idea. So the difference between limits concept is limit you're approaching, but derivative you are at that point. So remember that part, okay? Now we'll begin with the very first rule, which is power rule, and this is the most powerful rule which we are going to use in derivatives. So what I have done here to begin with, I've actually derived the formula from the first principle. So we'll actually differentiate the function f of x equals to x to the power of n. Now, if you have done binomial theorem, then you can actually expand the term x plus h to the power of n and then derive it. Now, if I want to find derivative for the function f of x equals to x to the power of n, then using the formula f dash a is equal to limit of this particular function fx minus fa over x minus a when x approaches a, right? So the x minus a approaches 0, very, very small amount. Now our function is x to the power of n, so I replaced f of x with x to the power of n, f of a with a to the power of n. Divide by x minus a, x approaches a. Now without going into how do I get this expansion here, x to the power of n minus a to the power of n is actually written in the factored form right there. You can verify this formula by expanding it. When you expand, you will see x times, let me just use another ring. When you multiply with x, then x times x to the power of n minus 1 will give you x to the power of n, correct? And when you do x times the next term, then the power will be x n minus 1, right? And when you multiply second time with a, x to the a times x to the power n minus 1, these two terms will cancel. You see that? When you expand, you'll find that. So all the terms in between will get cancelled. Only what remains is x times x to the power of n and a times a to the power of n minus 1. And you get what this is. Is that clear to you?
Yeah.
So this factored form is the correct form. You could verify expanding and simplifying it. Now, once we get this factored form, in that case, we can cancel out the numerator and the denominator factors, which is x minus a, right? So once you cancel x minus a, now you can substitute x equals to a, right? And then get your formulas. All the terms will be a to the power of n minus 1, a to the power of n minus 1, and we'll have n number of terms. There are n number of terms which are left. So it is n times a to the power of n minus 1, and therefore we get our formula, which is the derivative of f of x for this particular function x to the power of n is n times x to the power of n minus 1. Perfect. Now, I would like you to actually go through this method of proving power rule on your own. You should do it on your notebook, understand the whole thing. But it's very important and critical at this moment to understand the rule itself. Take it as a formula. If you have a function which is f of x equals to x to the power of n, in that case, the derivative is going to be multiplied by n and x power reduces by 1. Is that clear?
Yeah.
Okay, Amy. So we are going to use this particular rule now onwards to find the derivative at any particular point or derivative of the function rather than the first principle. However, remember, in your test paper, there could be questions which will specifically say find the derivative using the first principle. In that case, you have to apply the difference quotient formula and do just as we did for the cubic function right in the beginning. You understand?
Yeah.
And you may have to verify the slope of the tangent line. So this tangent line which I've drawn here, you have to draw like this, form a triangle, and then verify that the slope is exactly same as you got in your calculations. Perfect. So that could be a part of your question. Okay. So now we have already derived the power rule. You can make a note of this. And with this power rule, I would like you to now tell me the derivatives of these three parent functions. I've taken very simple parent functions to begin with. Now the question is, find gradient function using power rule. If f of x equals to x to the power of n, f prime x is n times x to the power of n minus 1. So that is the power rule. So we have to use this particular definition or the rule and find the gradient. So when you say find gradient at x equals to 1, first find the derivative and then substitute. To illustrate, I have solved question number 2 for you. So if the function f of x is square root of x, in that case, it is a good practice to write square root of x as x to the power of half. Perfect?
Mm-hmm.
Then the derivative f dash x will be bring half down, right? And x to the power of half minus 1. That is the formula. N times x to the power of n minus 1. So n in this case is half times x to the power of half minus 1. So you get simplified form x to the power of minus half. Minus half means it should be written in the denominator. So there you go. So that is your derivative. Is that clear to you?
Yeah.
So that is how you define derivative of the questions given in question number 1 and in question number 3.
Can you
Now,
leave it as the half x minus half in that form?
yes, in this case, leave it like this.
Okay.
Well, uh, that sometimes could be objectionable, but most of the time in derivatives, whenever you have square root, it will come in the denominator. So we kind of leave it most of the time.
Okay.
Okay, but I like you to check with your teacher also on this part, right? I have no objections, and normally I've seen in test papers it is okay.
All right.
So in this particular point, right? But as you know, we should not leave radicals in the denominator like this. We have to rationalize. So
Mm.
check with your teacher on that part, right? Kind of critical to check, since in test papers sometimes time is so critical that every time making this change may take a lot of your time. Okay,
Yeah.
it may not be worthwhile. So sometimes getting a hit of point 0.5 is better than trying to be perfect. So I see it the other way, right? Do you understand?
Yeah.
So in derivatives, I will accept this kind of an answer. Okay. Now part B is find the gradient x at x equals to 1. So just substitute x equals to 1 and you get the answer as half. You get the idea?
Mm.
And then the third part is verify your result drawing a tangent line. So I've done that also. Here is my tangent line. And if I just make a triangle from here to there, right? So we know this rise over run is actually half. Correct? So there is rise of 1 and run of 2 units here, minus 1 to plus 1. And therefore, the slope of the tangent line is half. So that is
Mm.
the exercise which you have to do for the other two functions. That should not be difficult, correct? Now, let's take up the next example. We'll build on our rule which we developed, which was called the power rule. Now we are also doing derivative of a constant times the function. So now we'll again derive another rule, derivative of a constant times the function. So let us say that the function f of x is equals to k times, k is a constant, another function g of x. Using the first principle, we'll find derivative. All the rules have been developed by using the first principle. So you go through this exercise and land up with the formula. Then you know this is the formula. So next time, apply the formula directly. Perfect. So if I have this particular function, k times g of x, applying this difference quotient, we know k is a constant. It can be taken outside as a common factor. Inside what you get is g dash x. Do you see that?
Mm.
So, so the derivative of a constant time a function is constant times the derivative of the function. Is that
Oh,
clear to you?
yeah.
Now,
It's
it's kind of
cool.
important at this stage because we learned that if we have x to the power of n, then the derivative is n times x to the power of n. But if I multiply that polynomial term with constant k, then there is not much change. I have to only add k, multiply by k. Do you get the idea?
Yeah.
So with that, we have written a general power rule. General power rule is that the coefficient remains as the coefficient. You get the idea now?
Hmm.
So that means that we can now find the derivative of any polynomial term very easily. Now, following this, we have two more rules which are called sum rule and the difference rule. Very useful, simple, and make a lot of sense. If we have two functions, if we add them and find the derivative, then it is same as sum of their derivatives. So either you add the functions and then find the derivative, or you find the derivative and add the derivatives. You get the same result. Perfect. Do you understand this point?
Yeah.
Means that if I have a polynomial which has many terms, I could actually find the derivative of each term and add it.
Oh,
Right? So that helps
yeah.
us to actually find derivative of any equation which is of the kind of a polynomial. Is that clear to you?
Yeah.
Now, one more important thing is that the binomial formula is very useful formula. Normally, that formula is defined for n, where n is a non-negative integer, right? When we learned about Pascal's triangle and all,
Yeah.
n was 1, 2, 3, 4, right?
Hmm.
There is a very special case, we call it Maclaurin series, where if we are saying a plus b, or we are saying x plus h, in our case, h is very, very small. If
Yeah.
the other term h is very, very small, then that formula works for all real numbers. So n could be any
Um,
real number. Is that clear?
yeah.
In calculus, it works for all real numbers because always we have the term h, which is very, very small.
Oh, okay.
And
Yeah.
the formula works for every function because of this reason. So be careful. This is a very good note. You need to understand. So let me stop sharing and discuss with you at this stage, Amy. The most important point here is we derive the formula using binomial theorem, right? Where
Yeah.
n is defined as non-negative integer. But a plus b, if b is very small as compared to 1, then that formula also works for n being a real number. It could be -1, -2, it could be half, it could be 3 over 2, whatever, right?
All
That is
right.
Bechdel series, also known as Maclaurin series, right? Since we are not there at Maclaurin series, we'll just use the formula, right? And the
Yeah.
and that is how, we just had a factored form. We didn't derive it. And now we are saying n could be any real number. That makes sense. So not only polynomials derivative we can find, but we can find
And,
derivative of any functions.
okay.
It makes sense.
Yeah.
So let's
Makes
get back to
sense.
our screen now. And that could be a question. Sometimes they will give you, and I've seen it many times for GCSE level A. They say,
Oh.
yeah, they will write like this: 10 plus 5 to the power of n, and they are using the derivative and finding the answer. And they say, this doesn't match with the correct answer. What is the reason? Because the number 5 is not very, very small. That's the reason.
Oh.
Correct? So you
Yeah.
have to factor out that some coefficient, make that 5 very, very small. You get my point?
All right.
And
Okay.
then use the derivative formula, and whatever you
Oh, yeah.
factor out, it has to be multiplied by that term.
Oh, yeah. Don't
So
forget that
remember
part.
this. This is excellent question which is always there. Sometimes students really struggle to understand, because by the time we complete this course, you'll forget that from where we started with n, it was a non-negative integer.
Yeah.
We started using it as a real number.
All
Why?
right.
Because of h, which was very, very small. Okay, if that is not small, we cannot use it. Remember that. Okay.
Yeah.
Okay. Now let's continue with the screen. Let me share that again with you. There we go. Share. Right. So, so you understand now that we have a power rule, we have a constant rule, we have sum and difference rule, and that makes our life very simple. Now we can have derivative of almost all the functions, right? Or
Yeah.
let's see how to work with trigonometric and logarithmic and exponential functions later on. But at present, we know how to do with other functions. So here I have taken few examples for you. Question number 2 is the equation of tangent line. Most of the time, Emmy, we are only finding equation of tangents, equation of normals. Then when you have an equation of a tangent, let's consider this graph, which is graph of x squared uh, cube root, x to the power of 2 over 3. Let me read the question first. It says, determine the equation of tangent line at P, 1, 3 on the curve f of x equals to 3 times x to the power of 2 over 3. Now, we can use the power rule straight away. We have the function here. So first thing is always write in the index form, x to the power of 2 over 3, so that you can bring this 2 over 3 right there, right? The
Mm-hmm.
constant 3 will remain as a constant, correct? Okay? And then to the
Yeah.
power, take away 1, 2 over 3 minus 1. You get your answer. And that is the derivative, which is this particular expression. Perfect. So if
Oh.
you want at point x equals to 1, substitute 1 here, so you have a 2 as the derivative at 1. That means the rate of change of the slope at this particular point for the tangent is 2. Once you know the point slope and the point, you can use the equation, which is, point form of equation, y minus y1 equals to m times x minus x1. And there you go. You get the equation of the tangent line. You see how simple it is now?
Yeah. It's quite straightforward.
Now, let me ask two more questions based on this. This is your tangent line. Your test question could
Mhm.
be find equation of the normal at this point. So that could be the normal, correct? For
Yeah.
normal, we have to only flip this negative reciprocal of the slope. We'll get normal. So you
Perpendicular.
read question number 4 for me, Amy. That is question for you.
So determine the equation of normal at P. Find x-intercepts of the normal and the tangent. Find area of the triangle PQR where Q and R are the x-intercepts.
Perfect. So these these are my points. Let's say P, I'm just saying point P is here, right? PQR. Let me write down like this. PQR. Is it okay? So somewhere we'll have an x-intercept. Is that clear to you?
All right, yeah.
And there you have a triangle. You have to find area of the triangle. So this length is the base and that is your height, 3.
Oh.
Half base into height, you get your area of this triangle. Very popular question. Always seen in GCSE test papers, level 1. Absolute necessity to solve. So that is the question which you have to tackle. And you have
Wait,
to
so
do it on your own, okay?
do they not give, so they don't give that normal or anything, we would have to draw it?
Yeah, you have to draw it. They
Oh,
might give
okay.
you graph at times. They might, yeah, they'll give you the graph. They'll give you the graph. Yeah.
Oh, I meant the
So,
graph, I just meant that line.
no, you have to draw that.
Yeah, okay.
But, calculate it. So when you get the equation y equals to 2x minus 1, you can find that the x-intercept is when y equals to 0. Substitute 0 for y, and you get x equals to minus half, which is this. Is that clear to you? So
Yeah.
get the equation of
Okay.
normal, get the equation of tangent, find your points, and then you know the difference between these two is the base, and height is directly given by the y value of the point, half base into height. I've provided you the solutions answer, right? So check with your solution, all these answers.
Okay.
Now we are almost running out of time, so let's move through a few more examples. Question number 2 here is equation of tangent line again. Now this is a second type of question. Find the points on the curve f of x equals to minus x cubed plus 3x squared minus 2, where the tangent is horizontal. Horizontal means what is the gradient here?
0.
0, perfect. So just write the derivative, which will be 3 times x squared. 3 times 2 is 6, 6x. And equate f dash x to 0, solve for x. We get two values, x equals to 0 and 2. So you get both the answers. So these are the values of x equals to 0 and 2, where you have horizontal tangent. And these are also turning points. Get the idea?
That's really cool, yeah.
Good. Question number 5, read it. This is for you again.
Find equation of the normal at x equals 1 on the curve of f of x.
Correct. I'd like you to take a picture of this page and also the previous page with your cell phone. And that will be your homework. Okay, so there are actually 10 questions for you.
Got it.
Got it? The next page is right there. So take this picture. And the very first page, also take this picture.
Yep.
Okay, great. So now I've taken a practical example on rate of change. Can you read the question for me, Amy?
Yeah. A spherical balloon is being filled with air. What is the rate of change of the radius of the balloon when the area is changing at a rate of 80 pi centimeter squared per centimeter?
So this time the gradient is given to us. The derivative is given to us. We need to find what the radius is going to be. Now we always say dy dx, but the function name could be different. Here the function name is area. So we'll write a, and r is our independent variable r. And the formula is 4 pi r squared. So we'll begin with the function, which is ar equals to 4 pi r squared. Derivative, we'll use the power rule combined with the constant rule. So 2 times 4 is 8. So we get 8 pi r. 2 minus 1 is 1. Do you get it? There we go. We have the derivative, 8 pi r.
I thought pi was a constant.
Yeah, so pi remains as pi. 2 times 4 is 8, 8 pi. Got it?
Oh, would it not be? Oh, I thought it would be like 0 or something.
No. It is a constant. 8 and pi is a constant. So you will multiply by the constant. R squared derivative is 2r. So 8 pi times 2, 4 pi times 2 is 8 pi and r. And now you are given that the gradient actually is 80 pi. So equate 80 pi with 8 pi and you get r is 10 centimeters. Done. Okay. Take a picture of this page and read question number 6.
Find the rate of change of volume of the balloon when the radius is changing at the rate of 80 pi centimeter squared per centimeter.
So this is the question you have to do. Take a picture and then we'll get to the last question. The last question here is, Your homework.
Ah,
So take a picture of this also. You need to answer these questions, and in our next meeting, we are going to discuss all the solutions. I'd like you to actually answer all these questions, share with me what you have understood, what you have not understood. Okay? And
okay.
then from here, we'll move forward to the next chapter and we'll discuss product rule, quotient rule in the next chapter. So we're done with the power rule and related rules. Now, Amy, could you summarize what we have learned today?
Yeah.
Yes.
So to start off with, derivative. We learned about so from the power rule, how do we get to that? So for most of the rules and things that we learned, we're forming it from the difference quotient formula, and we're always deriving it from that. So that's a really good thing to do, because in exams and stuff, if let's say you forgot the power rule, the difference quotient formula is always going to be there for you
Correct.
as backup. Even if it's longer, it's still always accurate. So we got the power rule, f of x equals x to the power of n. So the derivative of that would be nx, where n minus 1.
Good.
And then if you had f of x, ax to the n, it would be a times, the derivative of that would be a times n times x, then n minus 1.
Perfect.
And it works for everything. So
Yeah.
that's cool.
And we have to take care of tangents and normals in most of the cases. And we
Yeah.
need to practice with examples which involve both tangents and normals and the triangle form thereafter. So the third point could be the x-intercept. So most of the time, what I've seen in your test papers is that you have to work with the y-intercepts, x-intercepts. You'll always get a triangle, find the area of that particular triangle. Sometimes
Yeah.
we may have to work backwards. We are given the rate of change, and we may be looking for the points which will give us that rate of change. That could be sometimes tricky. So with that, Amy, I think we can wind up today's session. Try to do all those 10 questions which are there for you. And in our
Yeah.
next session, we'll actually review what you've learned. If there are any doubts, let me know. Also do all the questions from your exercise, since I've seen most of the questions, this is the part, right? So
All right. Okay.
this is the major part for you. And in our next session, we'll learn about the product rule, the quotient rule, and then see how to work with those rules and do derivatives or more complicated functions. Okay? Hi, Amy. How are
Thanks.
you doing?
I'm all right. How are you?
Good, good. So in the morning, we had a session on understanding how to find derivatives using power rule. Did you really understand that lesson?
Yeah, definitely. I got the concepts.
Okay, that's good. Any particular questions in your mind which you want me to clarify before we move forward?
Not yet.
Okay, great. So,
Yeah.
did you get enough time? Because I didn't really give you much time to solve some of those questions. Did you get enough time to do some of them at least?
Yeah.
Oh,
Some of
that's
them.
some of them. That's good. That's good. So, what really helped you to do all some of these questions in such?
So it was definitely the lesson that we just had, which was using the power rule and things,
Okay,
those concepts, and putting them into index form made it much easier to work with. So that was good.
okay. So let me share the screen with you. We'll begin with our what we learned in the morning, and then we'll move forward towards solving the questions. Is that clear?
Yeah.
Okay. So Abby, this time I'd like you to, in short, explain me the screen which is before you, and then we'll move forward and then discuss the questions which we need to answer.
Right. So I just learned that the dy over dx is, I don't know how to say it. It's Leibniz notation.
Okay.
Is that how you say it?
Yeah.
Yeah.
Let me.
Um, and the formula is still the same. It's still the difference quotient formula. That hasn't changed. It's just what we learned was the f of x, the derivative form is still finding the gradient, but it's just the same formula.
Correct.
So that's good.
So the gradient formula or the instantaneous rate of change formula is exactly what the derivative is. So derivative is
Yeah.
another name for the gradient. And in this unit, we learned about the basic concept of derivatives, the notations, whether the function is differentiable or not. We derived the formula for power rule, constant multiple power rule, and that combination gives you a much more power to the power rule. And then we also learned about the sum and difference rule. And then we took up examples based on tangents and normals and rate of change. Perfect. And as you were saying,
Mhm.
the derivative concept basically is giving another name to the gradient, and the gradient concepts will now be utilized to find the derivatives. And when we use these concepts, we call them first principle. So in your test paper, if you have a question saying, find the derivative using the first principle, then you have to start right from the very beginning, as you have been doing for gradient or instantaneous rate of change. Now here's a screen to about the notation. So tell me about the notation of derivative.
So if it says, so as you highlighted, x equals a, so if it's f of a, it means it's at a point.
Yes,
Um, so derivative is at a point, whereas when we were doing limits, it's all about you're approaching a value.
yes. Here we are at that point. So that point should be defined. It cannot be a whole and asymptote. So it has to be defined. If it is not defined, then you cannot find derivative at that point. Now, derivative should be treated as a function itself. So, derivative of a function is a function. So, when we say f dash a, it becomes a value at each point on that function, right? So, generally, we write f prime x or f dash x, right? So, these are the two notations which we use popularly, prime or Lagrange notation and Leibniz notation. So, prime notation is writing f prime a or f prime x, and Leibniz notation is dy dx. Now you have to be careful. Dy dx means differentiate the function y with respect to x. That's what it means. So instead of y, we could have f of x, g of x, h of x, anything, right? So d dx is actual d dx, right? So d dx of y, d dx of f of x. But when you combine them, you say dy dx. But basically, it is the operator is d. Okay, we say d dx of ax, d dx of f of x. Is that clear?
Yeah.
And then we took up an example saying, how do we solve questions on derivatives where we need to do with first principle, right? So this is using first principle. Perfect. So, Amy, can you explain me this particular screen? What are we doing here?
Right. So given that f of x equals x cubed plus 1, find derivative with respect to x. So f dash x using the first principle.
Perfect.
So because it
Yeah.
clearly states.
Give me 1 second.
Oh,
When
sorry.
yeah, thank you. Sorry to interrupt you. Now, A is derivative with respect to x. This is the correct phrase which has to be used, right?
All
Derivative
right.
with respect to x and f prime x. Do you see that? It's the function using first principle. You get the whole thing, right? So that's how
Yeah.
to read. Even if I write f prime x, derivative with respect to x. Is that clear?
Oh,
Okay.
okay. Yeah.
Let's continue with it. Part B.
Oh, and then the gradient of the curve at the point 2, 9.
Correct.
So because it clearly states that you need to find the derivative using the first principle, you have to use the difference quotient formula.
Perfect.
And then once you find it, it's asking for the gradient of the curve at that point. So all you do is take the value of x, which is 2, and just sub it in, and you get the gradient at the point 2, 9.
Perfect. So let's move on to the next screen. So what is this note telling us about?
Uh, oh, okay. This is quite new to me. So,
So dy dx
yeah.
has an advantage since when we are saying dy dx, we have actually said about what is the independent variable and what is the dependent variable. In this case, x is your independent variable, y is your dependent variable. We'll say differentiate function y with respect to x. It means this. Now, when there is a single variable, then whether you use prime notation or this particular notation, it doesn't matter because there is only one variable. However, if in an equation you have more than one variable, then we have an advantage using dy dx. Is it clear?
Oh,
So that's
okay.
a clear
Yeah.
advantage. But in writing convenience, f prime x is better. Now, the next screen was about existence of derivatives. Can you explain me this concept?
Yeah. So we said the conditions which like functions are not differentiable are at corners, cusps, vertical asymptotes or tangents, the jump discontinuity as we see with the piecewise function at endpoints, which is not there but is mentioned before, and at holes.
Correct.
Yeah.
Then we had a derivation for the power. Now, this formula may not be very familiar with most of the students. However, you can always expand and check whether this works or not. Once you apply this formula, we are using the first principle to find the derivative rule using a polynomial. So, Amy, can you explain me this particular part, power rule?
So what we did was we used the difference quotient formula in order to derive the power rule.
Yes.
So we just subbed in, so where it says f of x equals x to the power of n, we just subbed that in as limit as x approaches a. And like you said, we expanded it and cancelled the common terms. And finally, you get to the result of f of x equals nx to the power of n minus 1.
You're right.
Which n has to be belongs to all real numbers.
N belongs to all real numbers. Now that brings us to a very important note, and that is when you use binomial formula, n is non-negative integer. However, most of our cases, the value x plus h is very, very small. Now, this small value of h, when that occurs, in that case, the binomial theorem formula can actually work for all real numbers. Now, n could be any real number. We can apply this formula if the value of the other variable, other constant is very small. So,
Mm.
in calculus, normally, we'll have a plus h, where h is very, very less than 1. And therefore, n could be any real number. So some of you who have done Maclaurin series will understand this, but otherwise, take it as a rule for now. Okay? So
Yeah.
let's move on to the next question. And these were the real questions for you. So how do you find answering question number 1 and 3? We had already discussed how to do these questions with the help of question number 2.
Mm.
Explain me your
So,
solution for question number 1.
so with question 1, what I did was using the power rule. I just did 2 times x, and then 2 minus 1 is 1. So it's just, so you have to use the right words. A derivative with respect to x equals 2x.
Perfect. That's correct. And then you can
Then
substitute x equals to 1,
yeah.
find the derivative, and to check, you may draw a tangent here and check the slope of this particular tangent line and verify that the slope is 2. Correct?
Yeah.
And that's what you do with the other function, which is the reciprocal function. So if you're done like this, it's perfectly fine. Then we introduce you to another rule, and that is when you multiply by a constant any function, in that case, the derivative is multiplied by the constant itself. So the important thing which we learn here is that we could actually now extend our power rule. If the function is multiplied by k, now the function becomes k times x to the power of n, and now the derivative will be n times k times x to the power of n minus 1. That gives you a huge vector. In addition to this, we also have sum and difference rule for derivatives. That is to say that sum of two functions and then their derivative is same as sum of their derivatives. And
Yeah.
also, difference of two functions and the derivative is same as difference of their derivative. Now, once you combine all these rules, you can now differentiate any polynomial, since polynomial has terms which are added or subtracted, and you can now find derivative of any polynomial without any problems. Secondly, we have also seen that n could be any real number, and therefore we can also take care of other functions like surds. Is that clear?
All right. Yeah.
Now we have an example here. So could you tell me the example and your solution for question number 4?
Yes. So, should I read the question?
Yes.
Yeah. Determine the equation of normal at P. Find x-intercepts of the normal and the tangent. Find area of the triangle PQR where Q and R are the x-intercepts.
Correct.
So what I did was equation of the tangent. Well, the steps are given there, which is y equals 2x plus 1.
Correct.
And so we have to find the normal. So we need to do, because we need to find it perpendicular to it. So it has to, you have to find 2 times what will give minus 1. So it's minus a half. So I did y equals minus a half x plus c. Then I subbed in the value, the 0.13.
Yes.
And when you put those values in, you get c as 7/2. So the normal equation, the equation of the normal at P is y equals minus a half x plus 7/2.
Correct.
And then it says find area of triangle PQR where Q and R are the x-intercepts.
Correct.
So I was a little bit confused how you got the point R.
Okay. So once you get this equation, y equals to minus half x plus 7/2, at x-intercept, y is 0. So if you equate this to 0 and solve for x, you can bring this here, multiply by 2, x equals to 7 is your answer for. So you have 7 as your x-intercept for the normal.
All right, that makes sense. Yeah.
And I mean, no, so 7/2, I'm so sorry. When you do that, what do you get? You get 7, right? Is it that?
Yeah.
Maybe again. So you bring it, multiply, you get 7. And now the base is how much? Base is 7.5, correct?
Yeah.
7
and then you
this,
times it by
0.5 this. So you have 7.5 times half times the height. Is that clear? And height is the point P, which is 3. Is that clear to you?
Yeah.
Try this with 3. So then you should get your answer of 8. Perfect.
Wait, 7.5 times 3
is
22.5. Yeah, then times 0.5.
Yeah, the answer may not be correct. We may have to recheck this calculation.
I got 11.25.
Yeah, I did some rounding here. So whatever you're getting is correct. So you have to add 7 to this side. So when I write equation to 0 and multiply, we get 7. And so what we get here is 0.5 is the x-intercept here, right? So total base is 7.5. We are going to multiply base times height times half. Height is for us, right? And you get your answer. Do your calculation. Is that clear?
Yeah.
We'll have a similar example at the end, so we'll confirm our process with more additional questions. Is that clear?
All right. Yeah.
Perfect. You have understood how to do it. Next question, please. Can you explain how to do the question and question number 5?
Right. So find the points in the curve f of x equals minus x cubed plus 3x squared minus 2, where the tangent is horizontal. So we found the derivative, which was minus 3. So we got minus 3 because we did minus 1 times 3, and then x, and then 3 minus 1, which is 2. So you get minus 3x squared. And then you do 3 times 2, which is 6, and then x to the 1 is just 1, so 6x.
Perfect.
And then, so the horizontal tangent, So if it's a horizontal tangent, it means the gradient is 0.
Perfect.
So we made f of x equals 0, and then we just found what not f of x, the derivative,
Yes.
derivative with respect to x is 0. So
Correct.
then we just found that, we subbed it back in, and we get two values for x,
Yes.
being 0 and 2. And
Perfect.
as you look on the graph, when you look at the point 0 and 2, they are the turning points.
Yes.
Which makes sense because the
Perfect.
gradient is 0. Right. And then it says, I was a little bit confused here. So find the equation of the normal at x equals 1.
That is an
So
F.
x equals,
So at point
yes.
1, we can again use the same formula which we derived at f dash 1, find the slope, right? So at this stage, you have to substitute
1.
1 in the particular formula, which is minus 3, 1 square
I
plus.
did, but it doesn't get the answer that you put.
Oh, is that so? Okay.
That's why I was so confused.
Okay. Oh, that's fine. Yeah, we'll check the answer because I hurriedly wrote some answers here. We had a session in the morning, but you didn't check it. Okay. That's very good. So you got, what is your answer? Tell me.
Yeah, so I got 3 plus 6 and 9. Oh, no. So I was doing that, and then because I saw your answer, I was like, oh, I'm not getting anywhere near that. So I just thought the whole thing was wrong.
Oh, don't worry.
But what you do is after you do that, once you
Yeah,
find the gradient, yeah,
correct.
I'll just do that.
Do the normal, redo it. Okay. And
Yeah,
that
I'll
is what
tell
we are.
you later.
So in this particular question, we are looking for find the equation of normal at x equals to 1. So use this particular formula. Substitute x equals to 1 here. So as soon as I do that, we get 6 minus 3, which is 3. So slope is 3. The gradient of this particular line will be minus 1 over 3, right?
Mhm.
And then you can use this slope and the point and find the
And
equation.
sub it in.
And once you
Yeah.
do that, you will get some answers which may or may not match with this anyway. Confirm with me, okay? Uh,
Okay.
that is the whole question. So it was good that you actually got only 15 minutes to do the questions, and you did a great thing. You at least did some of them. And now here is the next example, which is example number 3, Emmy. Can you explain me this one?
Yeah. So I'll just read the question quickly.
Yes.
A spherical balloon is being filled with air. What is the rate of change of the radius of the balloon when the area is changing at a rate of 80 pi centimeter squared per centimeter?
Perfect.
So surface area of a sphere, we know is 4 pi r squared. So we made the area bracket r equal to that, where r is the radius.
Yes.
And then so here what we did was, so the derivative, you would just bring the 2 and do 2 times 4, which is 8, then that'll just be 8 pi r.
Yes.
So then we equate the 80 pi centimeter squared per centimeter to 8 pi r, and you get the radius as 10.
Perfect, because that is given to us. And we need to find the radius when the rate of change is 80 pi. And so we got radius as 10. Now, how will you do question number 6?
So we found the rate of change of the volume as 4 pi r squared,
Yes.
right? So then we just sub in because we found the radius 10
Yes.
into the formula, and you get 400 pi.
Perfect. We did this particular thing, rate of change of volume, earlier in rate of change, chapter 1, correct? You remember that? We did it with
Yeah.
first principle. Now, when we're talking about derivatives, you know the volume is 4 by 3 pi r cubed. When you do the derivative, that 3 and 3 cancel. You're left with 4 pi r to the power of 3 minus 1, which is 2. And you get 4 pi r squared. And when you substitute r as 10, you get your final answer of 100 pi. And the units will be centimeter cube divided by centimeter. Okay, that's kind of important, which I've not mentioned here. However, that is most important to mention. Here, now we have 4 of our good questions on this particular unit. Strictly speaking, these are the type of questions which we are expecting in a test paper. Now, in this short period of 15 minutes, I don't expect you to answer all 4 of them. So what I did in these 15 minutes was I actually wrote the answers for these 4 questions. I'm going to share those solutions with you. Okay,
I did some of them. I
that's
did 9 and
okay.
8. Yeah.
Okay, so you explain me what you did, and that way it'd be great. So the idea here is
Okay.
in the morning we had a session on understanding the derivatives and how to apply the power rule, even the derivation of power rule, which you saw in the first of this particular video, and we had some questions to work with. And in between, we had about 15 to 20 minutes to work on these questions. And Amy, let me really appreciate you on this part that in your 15, 20 minutes, you did a great job.
Thank you.
Yes.
Just
Now,
rushing.
4 questions are actually from real test papers, and they are not easy questions. Question number 7, can you read that for me, Amy? And then we'll discuss your answer.
Okay. Find the point on the hyperbola xy equals 27, where the tangent line is parallel to the line y equals minus 3x plus 2.
How did you do this question?
I mean, I started off by doing a quick sketch.
Yeah.
So y equals minus. Oh no, that's not the right question. Oh no, this one. So I did a sketch and I got 2 lines like this, and the tangent line is at a point. And finding the point, I don't know, because the gradient is the same because they're parallel. So I
Okay.
got that.
Okay.
Then
I'll discuss this solution just now with you. Question
okay.
number 7. So first thing we have to do is we are given an equation which is xy equals to 27. We have to write it in the form what is y equals to, right? That is our first step. So,
Oh,
so here what we see is that the value of y is, when you rearrange this, can be written as 27 over x, right? Somewhere here I've written. So when I say xy is 27, then y is 27 over x, correct?
yeah.
Now we call this kind of an equation as an explicit form of equation, where you isolate one variable and we say y is dependent on x, okay? Then finding derivative means dy by dx, applying the rule. X is to the power of minus 1, correct? So I've rewritten this as x to the power of minus 1, bringing minus here, and then minus 1 gives me minus 2. So that goes into denominator. So the derivative is minus 27 over x squared. Now, in the later half of this question, we are saying where the tangent is parallel to this particular line. That means this slope should match with minus 3, correct? So
Oh,
we have equated minus 3 with minus 27 over x squared. And when you do that, you can find the value of x squared and do your calculations. You get 2 values, which are plus and minus 3. You can plug in plus and minus 3 in this particular formula, which is your function itself, correct, to find the y value. So y is plus and minus 9. So you get these 2 points. So for the better understanding, I've drawn this particular function, which looks like a reciprocal function, where y is equals to 27 over x. So that is your reciprocal function, and these are your 2 points. As you can see, we have our tangent lines at these 2 points as shown. Perfect. So you understand, find the points on parabolas. We found the points on parabolas where the tangent line will be parallel to the given line. Since we equated dy dx with the slope of the line, we know they are parallel, correct?
do you mind explaining the first part again? The x y equals 27. So I
Okay.
get that you make y the isolate y, and then I don't know how you got it.
Then we did derivative of the function on both the sides. So when you do the derivative, dy dx is derivative of 27 over x. Derivative of 27 over x, 27 is a constant, right? X I wrote as x to the power of minus 1. Minus
Oh,
1 times x to the power of minus 2. That minus 2, x squared in the denominator, correct?
wait, no, I lost you. So 27x to the minus 1, I got that part. And then,
What is minus 1 minus 1?
oh, minus 2.
I
Oh,
wrote
okay.
in the
And then,
denominator x squared. Is that clear now?
yeah. Okay, cool. Thanks.
Now, Amy, in this particular question, we can do extension, and that is you need to find equation of those tangent lines, right? So you can use slope intercept form, You already know the points and you already know the slope, right? Now,
Mm.
all these questions could be extended in finding the x-intercepts. Is it okay?
Yeah.
And somehow the area of the triangle. That could be extended questions on such examples. Now let's take question number 8. So here is question number 8 along with answer. So could you do this part, Emmy?
Um, I mean, I did it, but I got it wrong.
Doesn't matter. So let's
Yeah.
go through this particular solution. Can you read the question for me, please?
Yeah. Find the equation of the normal to the curve y equals minus 8 over x plus 5 at the point A, 2, 1.
Perfect. So when we need to find normal, we know it is negative reciprocal of tangent. So we'll begin with finding the tangent. Tangent is nothing but gradient, which we are writing as dy dx. Correct? So we begin with our function, which is given to us, y equals to minus 8 over x plus 5. Y is minus 8 over x over 5, as I've written here. It really means x is to the power of minus 1. When you do the derivative, you get a negative and x to the power of minus 2. So I wrote it in the denominator, 8 over x squared. Minus and minus made this plus. Get the idea?
Mm.
So most of your questions in the test paper may involve reciprocal functions or radical functions, in which you may have to do this particular calculation and you'll have index which is negative, and then you rearrange it. You get the idea?
Yeah.
So that is kind of critical. Now, once we have the gradient of the function or the derivative of the function, we are given a point which is a, 2, 1. Substitute the value 2 for x and get the gradient or derivative at that particular point. That gives us the slope, right, of the
Mm.
tangent line. Normal will be negative reciprocal, so negative reciprocal is minus half of 2.
Yeah.
Correct? Now we'll find the equation of the normal itself. We know normal slope is minus half of minus half. So, and the point is 2, 1. Using this point slope form, which is right there, y minus y0 equals to m times x minus x0, we can sub it in, simplify, and get the equation of the normal. On this graph, you can see that that green line is the normal at the curve. Perfect?
So do you need to know that formula? Y minus y0.
Yes, this is a standard formula for point slope form of a line. So you can make a note of this.
Oh. Yeah.
Now, most of the time, students are using slope-intercept form, which is y equals to mx plus b. However, point-slope form of a line is much more easier to apply whenever we are finding equation of a line in standard form. So
Oh.
it is y minus y0 equals to m times x minus x0. You will notice one thing. What is slope? Slope is y2 minus y1 divided by x2 minus x1, right?
Mm.
So just bring this term in the denominator, you get the slope, right? So m is y2
Oh.
minus y1 divided by x2 minus x1. Here,
Oh.
it is that formula.
Yeah.
Basic formula, right? So we say y2 and y1 are my any general point, x and y,
Mm.
and the original points are given to you, which is in this case 2 and 1. Do you understand?
Yeah.
2 minus y1 over x2 minus x1 equals to m, written in a straight form, not a fraction form. Do you see that? It's a much
Mm.
simpler linear equation form of the same form. And it's a very useful form. You apply this particular formula now always, if you get slope in this form, cross multiply and simplify, you get standard form of equation.
Makes sense.
Very fast way of getting the equation of line. Much better than slope and intercept form y equals to mx plus b. Okay?
But it's still manageable with y equals mx plus c, but
It
it's just that not as easy and efficient.
Yes. It
Okay.
y equals to mx plus b, no harm. But this is
Okay.
better. And most books will follow point slope form actually.
All right.
So here is the extended question. Normals meet the curve at B. As you can see, we were interested in this particular point, but if you extend, it meets somewhere else also. as a part of exercise, you may have to work with this equation of normal and the equation of your function given to you, which is right there or here, whatever, and find the second point where the normal intersects. So that could also be a part of your question as part B or C. You understand?
Mm.
Find the equation of the normal and find another point where it intersects the original curve. So as an added exercise, you should do this on your own. So you
All
can
right.
take a picture of this page and try to extend question 8 also.
Mhm.
Here is question number 9. It didn't move. Sometimes there's a problem in Notepad, so I may have to restart this Notepad. So let me start this Notepad again.
Okay.
Yes, so okay, maybe I skipped question number 9. So I'll at least discuss question number 9. I didn't really, I may have it in my solutions here.
It's quite similar to question 4.
Yeah, it is very similar. So let me just go through this main file and I'll have it here, question number 9. Here we have. Perfect. So Amy, can you see the solution of question number 9 here?
Right now.
Not now. Okay. Where is the? Okay, let me share the screen. Yes, can you see question number 9 now?
Yeah.
Perfect. So can you read the question?
Find equation of the tangent and normal to the curve f of x equals x squared plus 2x plus 1 at the point A, 0, 1.
Part B, find the x-intercepts P and Q of the tangent and normal. Part C, find area of the triangle APQ. We did similar question earlier, and here is how you have to answer a question like this. It is a very critical question and very important question from test point of view. Perfect. So
Mhm.
to begin with, we'll start with the function itself, that is given to us as right there. Where you start, copy the function, find the derivative. Now we are interested at a point which is 0 and 1. Find the derivative at 0, and you get the derivative of 0 as 2. That really means that the slope of the tangent, which is slope m1, is 2 for us. Slope of the normal will be negative reciprocal, right? So my
Mhm.
equation of the tangent will be y equals to 2x plus 1. This is the equation of the tangent. We are linking these two. Is it okay? With slope of 2. Since we know the y-intercept, the beauty is the point is y-intercept. So we don't have to find b. We know b is 1. You get the idea?
Yeah.
So straight away we wrote 1 since we know that y-intercept is 1. That is for the tangent. And for the normal, since the slope was minus half, the equation will be minus half plus 1. Perfect? You get
Mhm.
two equations, right? We are
Yeah.
interested in finding the x-intercept for the tangent and for the normal. So continuing with the tangent equation, which was y equals to 2x plus 1, substitute y equals to 0 to find the x-intercept. When you do that, you can simplify this to get x as minus half. So that is the value, x of minus half here, correct?
Yeah.
For the normal, we did the same thing. Equation was y equals to minus half x plus 1, equate y to 0 to find the x-intercept. So when you do that, then you rearrange and you get x equals to 2. That is the value x equals to 2 for point Q.
Mhm.
You can clearly see your triangle here. Y-intercept A, x-intercepts P and Q. Area of the triangle is base half times base into height. Height is the y-intercept in this case, and difference between these two x-intercepts, you just add them up because one is negative and multiply by half to get your answer. So half times Add them up, which is half plus 2, correct?
Yeah.
Times 1, which is the height, a value. And you get your answer 5 over 4 square units. Is that clear to you?
Yeah.
Simple as that. That is how you have to answer such questions where both tangent and normal you have to find, x and y intercepts you have to find, make a triangle, get your answer. Perfect.
Mhm.
Here is the last question, which I think is one of the toughest questions. Can you read the question for me?
Yes. Find the equation of the tangents to the curve y equals minus x squared plus 2x, which pass through the point P29, the
Yeah.
point 29.
How will you do this?
Right, so I also did start by taking the equation, finding the derivative. So I
Yes.
got minus 2x plus 2.
Perfect.
Then it says, oh, do you sub in the point too?
Okay, now here's the critical part. If I sub in the point 2, what do I get?
You
Minus
get
2 square means minus 4, and 2 times 2 is plus 4. When you add them up, y is 0. Not 9. Not 9. Add 2, when you sum it up, you get 0. So that is that 2. It is actually the x-intercept for the parabola. So the point P29 is actually the external point. As shown on the figure, it is an point outside. Now,
Oh,
yes, in the question, we have a statement which says tangents. Do you see that part? Find the
oh,
equation of tangents. If I
yeah.
put a point on the curve, you can only draw one tangent.
One.
But if it is
I
up,
was wondering that.
there are two tangents. Perfect. So
Yeah, that makes
keywords,
sense.
keywords one, let me say tangents. That means outside point. So we treat this as an external point, as shown here. Correct.
Yeah.
So now the thinking changes altogether. Now we are saying that the derivative is minus 2a plus 2. Now what is the value of a? We don't know. We know it is a. So we'll assume. Now read this part.
Point P29 is not on the curve, so you say it's an external point.
Yes.
Two tangents can be drawn from this point to the curve. Yeah. So let the point on the curve be A, where A of f of x, or
FA.
A
Written A here. FA.
of fa, or A minus a squared plus 2a. Oh,
Substitute
because
a in your
you
equation.
subbed in a.
Yeah. So minus a square plus 2a. So that is your y2 value. Now slope between any 2 points is y2 minus y1 divided by x2 minus x1. So y2 is minus a square plus 2a minus the y value of the point, which is 9. Right? 20 cents this, y2 minus y1,
Yeah, yeah,
divide by x2 minus x1, and we get an expression which is minus 2a plus 2. Now, these two slopes should be same because we're talking about the same line.
yeah.
So now we equate them, correct? Now we
Mhm.
equate these two, we equated them actually. So this is how what we have got on this side, and this is that side, correct?
Yeah.
So these are same. So we equated them and then simplified our equation. You see that?
Yeah.
And once you simplify, you actually get the value of a. So that is your quadratic equation. We get two values for a, which are 5 and minus 1. For those two values of a, we actually get these 2 points on the parabola. So we have a tangent from external point at these 2 points. Now you have to find equation of these tangents. Get the idea?
All right. Okay. Yeah.
So to that, we know the derivative. Plug in a as 5, plug in a as minus 1 to get the derivatives at these 2 points, right? Plug in the value of 5 and 1 in the function itself to get the y value, f of 5 and f of minus 5, correct?
Mm-hmm.
So what we know here is, let's consider one particular line. For this particular line, we know that the point is 5 minus 15, and the derivative, this is for the line which is going downwards. So for this particular line, we know at 5, the y value is 15 minus 15, and the derivative is minus 8 as we calculate.
Yeah.
And for that, again, I use the slope intercept form, y minus y1 equals to m times x minus x1. And I found my equation to be y equals to 8x plus 25. You see how simple
Oh,
this equation is to use? We don't have
yeah.
to find the y-intercept and go back and forth. Straight away it could be used, right? Similarly, we use the second point and its slope with the external point and got the second equation.
Oh,
This question is
yeah, that makes
complicated.
sense.
I would like you to, Emmy, take a picture of this,
And
read
I'll do
my
it.
have a look and kind of understand what we've done. Okay,
Should I do this whole test paper in like
of
time
course,
conditions now we've
yes.
gone through it?
Do
Okay.
it independently. Yes, that is what you should be
Yeah.
doing. So these were the questions which remain as your practice test questions. So let me say
Yeah, okay.
this: that today, in first 25 minutes, we learned about derivatives introduction. We understood what is power rule, how it is to be derived, how the constant multiplier helps, and what is sum and difference rules. Combining that, we can actually find derivative of most of our functions, including all polynomials and even with radical signs. The idea
Hmm.
of using radical is that the binomial expansion works for small values of age, if that is one of the part of your terms, right? In your binomial a plus b. So
Yeah.
we could extend it for all other index also. Now, based on that, we had actually a couple of questions, 10 of them. And in these questions, we were trying to find what is the equation of a tangent at a particular point on the curve, what is the equation of a normal at a particular point on the curve, and where do these tangents and normal intersect, maybe x-axis or the curve itself. And sometimes we may form a triangle, and you may be asked to find the area of the triangle, and this chapter is all about this. Perfect?
Hmm. Yeah.
Now, once you've done this review exercise, tomorrow we'll take a test on this, and then we'll move on to power rule and the quotient rule for derivatives.
Okay.
Does it sounds good?
Yeah, that sounds good.
Are you ready for all that?
Yeah, why not?
Good. And if you get time in between, practice some questions from your book. If you have any difficulty,
Okay.
anything in your book, let me know. Right?
Yeah.
I think you should be able to solve 99% of those questions for sure.
Yeah.
Okay.
It's just about reading the question and like carefully and like looking for those hints, like you said, like even the simple thing when it said 2-9, I just
Yes.
assumed it was on the curve because I was like, oh, I don't need to check it. But then when we saw it was like an external point, I was like, oh, that changes everything. So
This
yeah.
is indeed very
Yeah.
critical, right? So anytime when you begin with this question, and that actually S gives you a hint. Do you understand? So
The
you have to
tangents,
be double
yeah.
sure whether your point is on the curve or not, right?
But it was like a typo. uh, yeah,
Yes.
so that caught me out. Never assume.
Never assume. Perfect.
Yeah.
Great.
Right.
Thanks a lot, Amy. And we'll end our session. Do you have any questions?
No, not so far. I just think that I'm going to go through all the questions now because you've gone through them, doing time conditions and see if I'll actually like grasp the concepts. Because I've seen many of the, like we saw in question 4 and 9, they're the same thing. It's just different in its wording. So if you get those concepts, then when it comes in actual exams, you'll be like, oh, I've seen this kind of example before, so I can just do it again. So
Perfect.
it's about getting the concepts, yeah. Practice.
Practice. Okay. Thank you.
Thank you
And
so much, sir. Oh, thanks.
yeah,
See you, sir. Have a good day.
you too. Bye.
Bye.